So the next condition monitoring technology that we will be looking at now is the infrared thermography. Infrared thermography. So we are going to look at what infrared thermography means, okay, and what instrument we can use to detect that infrared energy that will be coming from our equipment, and how to carry out the analysis. Okay, so that is basically that is the application of infrared thermography in our facility. That's basically what we'll be covering under this section. So infrared thermography, we are going to look at the infrared radiation and thermography, what it means, okay, so that we'll be able to appreciate its application. Then the application of infrared thermography, we are going to go through it under this section. Then the analysis technique, both quantitative and qualitative, we are going to look at them. Then, of course, some case studies. So these are the few topics that we are going to carry out, but we are going to dwell more on the analysis technique in the course of this section of our training. So infrared thermography, what does it really mean? Okay, so let us first appreciate infrared, what infrared is. If you look at your screen, this is the electromagnetic spectrum. Okay, so this electromagnetic spectrum, you see we have the visible range of the electromagnetic spectrum. That is the area, the range that we can sense with our sense of sight. So before that visible range, we cannot actually perceive those radiation, okay, with our sense of sight. Okay, then beyond the visible range too, we cannot perceive those rays or waves in that region. So immediately before the infrared or after the infrared, as in this case, we have the infrared region. Okay, we have the infrared region. Then before the violet, we have the ultraviolet region. Are we getting it? So we have the infrared and the ultraviolet. So our interest now is the infrared region. So all heated body, they emit waves that are in this infrared region. Okay, so that is why we are using this technology in trying to determine the condition of the equipment. So that's infrared. Then thermography. Thermo, something that has to do with heat. Then graphy, picture. Okay, so the infrared thermography actually looks at the heat energy that is coming out of a heated object or of a body, and then transpose that into a form that we can easily understand or perceive with our sense of sight, which is the thermogram. Okay, so the act of converting that infrared energy into a photographic image that we can perceive and interpret is what is referred to as infrared thermography. Are we getting it? So we want to know that we are looking at waves in the infrared region of the electromagnetic spectrum, as you can see on your screen. Okay, so we'll also look at the principle of that infrared imaging. As we go along, we have understood what infrared is. Okay, so now let us see how this infrared imaging is done. Remember, we said the infrared is something that we cannot perceive with our sense of sight. Are we getting it? We cannot perceive it, though we can feel it if we are close to the source of the energy, but we cannot see it. Okay, so let's take example of what we have on the screen, a saucepan on a burner. Okay, so as the saucepan is heated up, what happens? You see that heat energy, okay, will the saucepan will start transmitting that heat energy into the environment. Of course, if you touch on that saucepan, especially the conductive part, you feel the heat, or you take it close to your skin, you feel the heat radiation, okay, onto or radiated onto your skin. But you cannot see that heat energy as is leaving the saucepan. So that is what the infrared imaging will assist us to do. So is to convert what we are seeing physically into thermal image, okay? And this is what we are seeing here. So from looking at this thermogram, you see that the middle part of the saucepan, which is expected, is hotter than the circumference of the saucepan. Are we getting it? So the conversion, okay, of this, the heat energy that is coming from this saucepan into a form that is visible to the ordinary eye is what is called infrared imaging, okay, or infrared thermography. So we have instruments that assist us in doing that. That is the infrared camera, which is what you are seeing here, okay, that will help to convert this heat energy into a form that we can actually perceive or see. So this is a sample of the infrared camera, okay. So this is an example of the infrared camera, and that is what you are also seeing in your screen, okay. So it is this camera that will help us to convert that heat energy as is coming from the heated source or the hot body into a form that we can really perceive or understand. So that is how we don't want to go into details much. Then what are the benefits of this infrared thermography? All what you are seeing on the screen, these are thermograms or infrared image, okay, giving us the heat distribution on that particular equipment or object that we are looking at, helping us to perceive whether the heat emitted from the body is normal or not, okay. So like here now, you see this is a flue gas stack, okay. So you are looking at the flue gas as it's being emitted. Ordinarily you will not see it. Are we getting it? But with the camera you'll be able to see that flue gas. Here also you see the distribution. We'll come to understand how to interpret this thermogram later. Then this is a tank, and we'll see the level of the tank, okay. So these are pipelines. Then you see the heat distribution on this pipe, showing that something is developing here. Okay, this is on electrical system, and of course we have the heater, and so it has a very wide area of application. So what are the benefits of this infrared thermography? So one, it is that this technology is very, very versatile. You see, what we have explained just now shows us that it has a very wide area of application. You can apply it in process, okay. You can apply it in, it has electrical application, which is one of the area where it is most widely used. It has mechanical applications too. You can use it, as we'll see later, use it to look at bearings, okay. So as the fault is developing on the bearing, definitely the heat emitted on that bearing or from that bearing will increase, which will eventually be transmitted onto the housing, which we will see clearly in the thermogram, okay. So it is a very versatile technology. It even have both security and medical applications. Okay, so we'll see all of this. So it's a cross-cutting technology, one technology that you can apply for the maintenance of your entire plant, okay, on various systems. It's just for you to appreciate or understand how it works and what you are looking at, okay. Then it also assists in early fault detection. So before the problem will deteriorate to the stage where it will cause failure, you would have seen it using this technology. Like this electric motor now, as an example, as we'll see later, the temperature here, okay, is a reflection of the winding temperature. So once it's rising beyond a level, we know we're already having issues with the winding. So before the winding phase, you already know. And then if there is any intervention, maintenance strategy that you want to deploy to bring it back to what is normal, of course, we will do that. Then the thermographic inspection is non-contact, does not involve you getting in touch. You can do it from a distance. Are we getting it? There are some camera that you can actually stand at almost 100 meters and you'll be able to get very clear picture thermogram from the objects that you are looking. And another beauty is that you do not need to shut down your process, okay, because we need the process to be working before we can take meaningful thermogram. It is non-contact, okay, and the information you will get, they are going to be live information real time, okay, as the operations are taking place. So that is what you are seeing here. From a distance, you are looking at what is happening on this transformer and you are seeing it on the screen of your infrared camera. Are we getting it? So it's a non-contact inspection method or condition monitoring method or technology that is very, so like we said earlier, is a technology that you need to collect information real time, so the equipment does not need to be shut down, okay, does not need to go off. So, and again, if the equipment, they are not working, it means that heat energy will not be there, so you will not see anything on with your camera or your thermogram, okay, that will be meaningful. So it needs to be working, the equipment needs to be hot, okay, operating normally before you can get something meaningful. So you do not need shutdown. So like we said earlier, it is very versatile, which means that it's a technology that you can apply on many systems or various systems in your facility. That makes it to be very cost effective. Remember, we said is a system that you can use to there is a technology that you can use to monitor your equipment when the equipment is working from a distance. So which means you can scan a very wide area, okay, of your facility for a very short time, in less than 5-10 minutes you scan. Then if there is any point of interest, you see hotspots and the rest, then you now focus on such points and try to analyze, okay, further to know why you are having such hotspots. So we said it before, for real-time visualization. So we have seen the benefit of the infrared thermography. So we want to look at briefly the application of the infrared thermography. Remember, we said this technology has an application that is cross-cutting, okay, various areas, mechanical, process, electrical, even instrument. We also said it can be used for security and medical purposes. Okay, so in your facility, if you have a facility like this, you see that infrared thermography can be applied in virtually every facet of this kind of facility, both the static equipment, the rotating equipment, and the instruments, your process. Are we getting it? Provided there is this thermal differences in various areas of your operation, or on the equipment that you'll be looking at, or on the process during normal operations. So you know the thermal gradient or thermal difference that is normal to your operations and what is not normal. Once it starts developing, you will see the clear difference. Okay, so you can apply it to your substations. As we'll see later, you look at your transformers, your circuit breakers, all the switchgears in the substation, even the bushings, okay, the point of connection, looking for loose joints or joints that are not properly made, okay. Undersized conductors, the application is numerous. We'll see them later as we go ahead in this program. So it also has mechanical application, like we said too. You can look it to monitor, use it to monitor your bearing. You can use it to look at your coupling to know if the coupling is developing faults. Okay, you can use it to look your compressor, whether the discharge is functioning properly. Okay, so we'll see all of the applications mechanically that we can use it for. Then on your process too, you can use it to monitor fluid flow. You can use it to monitor instruments, whether they are passing the right liquid, that is at the right time. Okay, whether valves are opened and what have you. Then we'll also look at other application of the infrared thermography. So you see that it's a very versatile technology that has a very wide range of application, as you have seen. So let us look at the electrical applications first and why it is very useful in our electrical system. So we know that from the point of generating the electricity, which is at the power plant, to wherever we are using the electricity, okay, you know, we need conductors. So it is conductor that will carry that electrical energy from the power plant to your substation, through to your, that is the transmission substation, through to your step down substation, all of your substation, and then to your facility point of usage. Okay, so you also need conductors even to your equipment to carry that energy. And you know that as you are loading the system, what happens? You are increasing the current that is flowing through those conductors. And since current is flowing through, it means that some amount of heat will be dissipated from the I square arrow effect. Okay? Being that the conductor have some level of resistance. All current carrying conductors, that is all conductors, I mean to say, the copper, if it is copper wire that is used, or aluminum that is used, okay, they all have some level of resistance. And if current flows through, there is bound to be the dissipation of heat energy, I square arrow. So that I square arrow that will come off in the form of heat during normal operations, with this camera, with the infrared camera, you'll be able to see that heat that is emitted from the equipment, because the energy will flow through the equipment, okay, from those conductors, and wherever it goes through to your facility, or even within your facility, wherever the current is running through. So with that, you'll be able to know what is normal. The normal thermogram, okay, will be established, such that when there is abnormality later, when you go out to take thermogram, okay, and reference it to what you have initially or what you know, if there are discrepancies or difference, of course something must be happening at that instance. Okay, so when you have, let me say, something like loose connection or connection that is not properly made, you see that the current as it's flowing through at that loose connection point, it will meet a higher resistance at that point than what is normal. Are you getting it? So that I square arrow increasing at that loose point or loose connection, it means that the heat dissipated at that point will go up. Okay, so overload situations will also generate higher heat than usual. Once you overload an equipment, you will see that since the current that will be flowing through will go up, the heat energy that will be dissipated will also do what? Go up. So you will see all of these in your thermogram and be able to deduce that you are having an overload situation. Okay, so because of the kind of conductor, that because of the fact that current flows through conductor, okay, you can use it in our electrical system. And since the current is flowing through that conductor, heat energy will be dissipated. We can use this technology to look at our electrical system to know if the condition is normal or abnormal. So like in transformers, we know we have windings inside this transformer, and during normal operations, current flows through the various phases of the winding. Heat is what generated within the transformer. So this heat that is generated will be absorbed by the oil, okay, the cooling oil or insulating oil that is in contact with the winding inside this transformer tank. Okay, so that oil will absorb the heat from the winding and bring it, the hotter oil molecules will move away from that spot where it absorbs the heat. Okay, and then the normal convention will be created. The cooler ones will go drop down to the position of the hotter oil, while the hotter oil will move out. Okay, so that normal convention will drive the oil into all of these cooling fins, as you are seeing. So in these cooling fins, the oil will now give off the heat that it absorbed from the windings, okay, to the body of these fins of the transformer. And this heat that is given here, the air molecules around, okay, both the ones that are trapped between the fins and outside, will absorb the heat from the body of the transformer and takes it out. So which means that as the transformer is working, these cooling fins expectedly will show some heat that is gives off heat, because that is its work. Are we getting it? So that heat, we can look at it with the infrared camera. Okay, when the equipment is working normally, we'll see, we'll see the thermogram later. So we'll see what a normal thermogram on a transformer looks like. Okay, so we'll see the temperature gradients on the thermogram and know that this transformer is working perfectly. Then if there are abnormalities happening or abnormal situation happening within the winding, of course that will make the heat dissipation to increase. And once the heat dissipation increases, what happens? The heat that will be transferred to the transformer fins, the body of the transformer, will also increase. So we'll see the thermogram showing increase in heat, which will give us an idea that something is wrong. All these fins, if they are blocked, okay, the thermogram will show that the fins are cool because they are blocked. So no hot fluid is flowing through or into them. Are you getting it? So that will tell you that something is happening. You have to do something to remove whatever debris that is blocking those fins. Okay, so on panels too, electrical panels, you can look at it, but we'll see the thermograms later. You can look at the loading on each of the lines. look at the connection points for hotspots. Are we getting it? So the all these terminals, you can look at them if the connections were properly made. And then the loading too. Okay, we have the normal thermogram. If the loading on the three faces are the same, the heat energy that is dissipated or emitted from the three will be the same. So the thermogram will be the same. So if it is not balanced, the load is not balanced, you will see that the thermograms from each of the faces will be different. Okay, so it's just for you to appreciate what you are looking at. Once you appreciate what you are looking at, you can apply it to so many areas in your facility. Then on mechanical equipment, as we said earlier, we will see the thermogram on a normal working motor. The motor also has winding, okay, and that winding has a direct, there is an insulation between the winding and the yoke that is coupled to this frame internally. Okay, so the winding transmits the heat that will be generated on it because of the current that is flowing through the windings during normal operations. So that heat that is generated within the winding will be transmitted or transferred to this body. Okay, so you see the heat coming out. So as we also see later, the cooling effect of this fan, you also see it. Then on the bearing end, you see it, as the bearing is working, remember the bearing on between the balls and the races, there is bound to be some frictional force, okay, which you try to reduce with your lubricating oil or lubricant. So that frictional force that is reduced will, even though it is real, will also generate some amount of heat, okay, that will be transmitted through the bearing onto the housing. We'll see that later. So from the infrared thermography, the camera will be able to see the normal heat that is generated when the equipment or when the bearing is functioning normally. So as the bearing is deteriorating, maybe as a result of fault on the rotor or on the equipment imbalance or misalignment, you'll see that the frictional force will increase, okay, and that will come out as increased heat. Even the bearings on the pump, are we getting it? All of them will show on the thermogram. Okay, so this is what you are seeing here for the electrical applications. Okay, so you see the thermogram. This is what we call the thermogram. Okay, it becomes clearer later as you are looking at. So, what are some of the electrical faults that we can detect using the infrared thermography? One is overload, as we explained earlier. Okay, if any of the lines is overloaded, you see the thermal energy that is coming from that line higher than others. Are we getting it? So that tells you that this line is loaded more than the others. Even if it is only that line that is there, you see the thermal energy becoming so abnormal, okay, along the line. Okay, there won't be any gradients. There will be even temperature along the line because the same amount of overload current is flowing through and the resistance on the conductor is the same. So you see the same heat dissipation, but you would notice that the heat that is coming out is higher than what is normal. Okay, so that will give you an idea that what you are looking at is overload. Then loose connections too. If any of the joints they are loose, all these connection points, if they are loose, that creates higher resistance, or joints that are not properly made creates higher resistance to the flow of the current. So as the current is flowing through that high resistance joint as a result of loose connection, it will come out as increased heat dissipation, okay, which will be different from what is normal. So with that, we'll be able to know that we have problem. Then unbalanced loads, as we said earlier, you will see that the phase that is carrying the highest load we have higher heat dissipation than the ones that have less loads on them. Then defective components. Okay, when the components are defective, especially electrical components, you see that the heat that is coming out will be given off from that equipment component will go up normally. Okay, or if the equipment has failed, it will just there will be no heat energy coming out from it. All of those are abnormal situations. Are you getting it? So it will look dead on your thermogram while you are looking at it from that distance. Even if the equipment appears to be working, the component will look dead, or the component will look overstressed. Thermal energy that is coming out from it will be higher than normal. So those are signatures of defective components. Then hotspots on electrical panels as a result of loose connection, that is poor connection, or high resistance joints. Okay, we will see all of those on the thermogram. Then overheated motors. As we'll see later, the motor have normal thermogram. Once the motor becomes overheated, we also see them. Transformer problems, as we have explained earlier, you will see them on the thermogram. So other potential faults on the electrical systems, okay, they can also show up as hotspots in the thermogram. So let's assume that we went into the field and was taking the thermogram or doing inspection of this particular circuit breaker. Okay, so on the screen of our camera, this is of our instrument, this is what we will now see. Are you getting it? So if you look at it, you will see that the heat energy that is coming from this middle cable, which is not visible to the ordinary eye, as you can see here, this is what the ordinary eye can see. This is called the visual image, and this is the thermal image. Okay, so to the ordinary eye, you will not know that something is happening here. Are you getting it? Then, but if you look at a thermogram, you know something significant is happening, and this is the spot temperature, which is what we are seeing about 104 degrees Celsius, which is high. Okay, so when you remove the ambient, the delta T will tell you that the temperature on this conductor is high. So this is a signature of overload, because you see that the temperature, there is no gradient. The temperature, the heat that is coming out is even. Okay, because if you carry this spot now, you see that you have the same temperature along this conductor. So this tells you two things. One, it is either this conductor or this line is overloaded, or this cable is undersized. But if you are very sure that the three of them are of the same size, okay, it means that this is overloaded. So you now carry out further check. You can come with your arm probe, okay, to take the load readings on each of the phase so as to confirm your suspicion. Are we getting it? But most likely you will see the overload. So no gradient, clear indication of overload. Then this is the thermogram from an electric motor. Okay, normal thermogram. Because if you look at it, you see the temperature gradient. Remember, we said the windings of the electric motor, since the winding is laid in slots, okay, though insulated, that heat that is generated within it will be transferred into the yoke and then to this frame. Are we getting it? So this frame is expected, when you view the thermogram, to be hotter in the middle, which is what you are seeing due to several factors. We will explain them later. So you see that heat, okay? Then around the bearing housing too, you see an increased thermal activity there. Okay, increase high temperature around the bearing housing also. Then if you look, you will see that here is cooler as you move away from the back end of the electric motor. So this is the cooling effect of the fan. Are you getting it? You see the cooling effect of the fan, then to the middle of the motor that is hot. Okay, then down to the other end shroud. You see the bearing signature. So this is what we term the normal thermogram of an electric motor. So if you see something like this, you know that the fan is working, the winding is working, then this is normal thermogram from an electric motor. So now what is left for you? During normal operations, when there are no issues with the electric motor, you will take this thermogram, okay, and use it to form your baseline information or baseline data that you will subsequently be referencing to. So you take all the spot temperature at the middle, which gives you an idea of what is happening in the winding. So let's assume that the spot temperature is around here, let's say about 60 something degrees Celsius, though when the camera, once you put on the camera, you move your spot, your cursor to this point, it will give you the temperature of that spot. Are you getting it? So you will know the temperature of that spot. Then you see the cooling effect of the fan very clearly. You can also go ahead to get the temperature of those spots. Then around the bearing housing, you get the temperature also. Okay? So subsequently, when you come and you take the thermogram or you do your infrared inspection, if this equipment is dead, there is no power supply to it, you will not see any of this signature. It will appear very cool like this. Are we getting it? And it's going to be even because the temperature of the motor then will be the same with the ambient temperature of the ambience. Okay, so that will mean that the motor is not working, no power to it. Then if you have something abnormal, maybe you have this temperature gradient is not there, everywhere is hot evenly, it means that the fan has failed. Are you getting it? Then if the spot temperature here is higher than what is normal, it means that you have issues. Maybe they may be developing issues with the windings. Okay, then if you have here the temperature here going up, it means that you are having issues with your bearing. Are you getting it? So that's how you analyze the thermogram to determine the condition of your equipment or the equipment that you are looking at. Okay, so this is another thermogram. You see clearly then there is something here too. If this equipment is overloaded, you see that the heat energy that is coming out from the thermogram will also go up everywhere on the motor, okay, motor frame. So this shows clearly that the three phases, they are overloaded, okay, but in most cases you see that the thermal the heat dissipated here will be the same as the heat dissipated on the other side, okay, of the circuit breaker, the output of the circuit breaker. So you have, once you see something of such, it means that the line is overloaded. So this is a thermogram of an overloaded motor. You see it? You cannot see this temperature gradient here. It's even possible that the fan has failed. Okay, so you will not see this temperature gradient here. See fully heated. Okay, again you have to look at the temperature also, because if this your camera setting is right, because if it's below, if your setting, your range is below the temperature that you are looking at, definitely you get something like this. But if it is within, okay, of course that will mean that this motor is overloaded. Okay, then if you look at this bushing and then look at the connection point, you see that there are no issues. Look at the various lines. Okay, you see that the thermogram, they are almost the same thing, which means that the loadings on phase 1, 2 and 3 is the same thing. Okay, but if there are issues, maybe poor connections, you will see them very clearly on the thermogram. We will see such later. So loose connections, you see loose connections like this is what you this is visual image. Okay, you definitely see nothing. Then but with the the infrared camera, this is what you see. So you see that there is significant thermal event happening around this fuse, okay, or this connection. And then if you look at it, you see that it is hotter here, and then as you move away from that spot, it becomes cooler. So you see that temperature gradient. So this temperature gradient shows you clearly that the heat is generated from here. That is the heat source. And as you are moving away from the heat source, the heat is going down. So that shows you clearly that what you are looking at is a loose connection. So before this will cause failure and shutdown of your facility, that will eventually result to unwanted downtime, okay, you can firm up the joints, make the joints properly, and then this problem will be solved simply by just tightening, okay, the bolt on that joint. Tightening the bolt here will just solve the problem. If it is something you can do while the equipment is working, fine, or else you shut down the equipment and then do your tightening and bring the equipment back online. So these are examples of loose connections on these overhead lines. Okay, so from where you are on the ground, you see that you have loose connections on the line. So here too, you see the temperature gradient. That shows you that this terminal is loose, which is not visible on this visual image. Okay, everything looks normal, but something that can destroy the breaker itself is happening there. That is what you are also seeing here, loose connection of the gradient. Are you getting it? Hotter at the connection point and then becoming cooler as you move away. That is for this breaker. Okay, so this is another thermogram showing loose connection of this joint. So simply tightening this properly, making this joint properly, will solve this problem. So when you see issues like this, it's just for you to firm the joints, okay, the connections, tighten them properly, and then the problem will be solved before it results to failure. So on balanced load, like we said before, when the lines are balanced, these are what you will see. Are you getting it? The lines are balanced on the face, so you see that the thermogram, okay, will be the same on each. The heat that is given off from each of the lines, they will be the same. So this shows that the phases are balanced. But when one is hotter or higher in heat energy than the others, shows that one line is overloaded, and one is cooler than the others, that one line is underloaded. So those are forms of unbalanced loading. Okay, so this is an example of unbalanced loading. Are you seeing it? So this one is carrying more load than this other two. So if it is something that you need to balance the load, of course, just merely balancing the load will solve this kind of issue. Okay, this is another example of unbalanced load. You see that this line is clearly more loaded than these two lines. Okay, so if the conductor is sized properly, this one is the same with all of these ones. It means that you have overloaded this line. So you have to remove some load and distribute them among these two to balance load. Then on PCBs, so when there are defective components on PCBs, you also see during operations, you also see the extensive heat energy coming out from that component that is defective. Okay, so we can also look at capacitor banks. So the capacitor that is faulty will either give us the hotspot to show that capacitor is developing some problems. You see the hotspot at the joint, or if the capacitor is dead, it will appear cooler while others will appear warm. Okay, so those are some of how you can interpret and apply the infrared thermography. So on electrical systems, it has a very extensive applications. Okay, and it is very, very, very useful on electrical system to determine developing problems, as you can see on your screen here. So I want you to determine what is happening here and what is happening here. Okay, and send your response to us. Take this as image 1, 2, 3, 4, 5, and 6. Okay, and trying to tell us what is happening there. Okay, so you see loose connection at that point, and also overloaded line. Okay, all of them showing clearly. So this is for an electric motor. So you see the thermogram, which is normal. You see the temperature gradient. You see the cooling effect of the fan. Okay, all of these are normal. This is what we've seen before. Okay, so this is for a fan. This is the fan now. You see the temperature gradient. Okay, see the cooling effect of the fan. Okay, so if this is normal and then nothing is happening, that is if it is not beyond the delta T designed for the motor or recommended for the motor. Of course, that motor is working perfectly. Then you can also use it to monitor coupling too, bearings, as we have said before. Then on the issue of the coupling, if you have misalignment force, remember that misalignment force, as the motor is trying to overcome it, you create more friction around the coupling. So you see increased temperature around the coupling, okay, than what is normal. So that will tell you that misalignment is developing around that coupling. You can also look at the bearings too on both the driver and the driven equipment. Are we getting it? So that is the inboard end. All of this will tell you, even the outboard end, all of this will tell you what is happening around the bearing housing. So for power transformer problems, we have discussed power transformers before. So this is the thermogram of a power transformer. Remember we said the winding inside the transformer tank. Okay, as you are loading the transformer, generates heat because of the current that is flowing through the conductor, which is resistive in nature. So that heat is absorbed by the oil. Okay, the transformer oil, the cooling oil within the tank, and that transfers the oil to this radiator or cooling fins. Are you getting it? So that heat which is transferred to all of this will now be transferred to the atmosphere. So you see cooling fans. Okay, these are cooling fans, which are these two. Okay, so when you take the thermogram, what you are seeing here is a normal thermogram. Are we getting it? This is the normal thermogram of a working transformer. So remember, as the oil, okay, the insulating oil or cooling oil is heated up in the transformer, absorbs heat, so that hot oil will naturally rise up. Are we getting why the cooler one will drop? So which means that you expect to see hotter signature on the upper part of the transformer, okay, which is what you are seeing here, while the cooler ones will be coming down on the transformer. So this is a normal thermogram. So if any of these fins they are blocked, okay, maybe this one is blocked and no cooling oil is coming into it, then you will see that that one will be dead. Are we getting it? To show that no oil is coming into it, will be cooler or very cool than the others. So, but if you look at this thermogram, you see that all the radiators, okay, they are all working. Okay. Now, if you also look, we have fans here. Okay, then these are the fans. Then if you look, you see that it is only one fan that is working. Okay, which is this, because that's the only fan that is winding is hot. Are you getting it? So all others are not working. It could be normal because you don't expect all of them to work, but as the heat dissipated or the load on the transformer is increasing, more of the fans they will come on. But if you expect that all of the fans should be on at this instance, okay, you see this one, only one of them is on, that tells you clearly that there is problem in with the rest cooling fans. Okay, so we have cooling fans here too. You can see it's working here. Are you getting it? So if there are hot spots here too, you will see them, loose joints or loose connection. These bushings, if you have cracks in any of them, you see them on the thermogram also. So that's a normal signature, and that is what you are seeing here. This is normal signature, okay, on your transformer. You have to have hotter oil above and a cooler one below because of the natural convection, okay, current that is always flowing in the transformer. So look at this transformer cooling fans. You see this one obviously is not working. All the others they are working. See, it's cool. Then look at this radiator. Okay, you see that it is clearly blocked. No cooling oil or one transformer oil coming into it, so it is blocked. And you can see that the thermogram from it is different from that of the others. So you can safely conclude that this radiator is blocked and it needs to be cleaned up, okay, to remove the debris. Then you look here, you see that hotspot is developing. Are you getting it? So all of these are some of the way you can apply or interpret those thermogram. So on this circuit breaker, this is an hotspot, loose connection, most likely is what is causing this, because you can see the gradient. Okay, so hotter at the point of the source of the heat energy, and then becomes cooler as it's moving away. So on mechanical applications, we have discussed this before. On looking at the coupling, this one is guided so we cannot see it. Looking at the bearing, looking at your pump, okay, looking at the pump casing and what have you, okay. So even looking at the valves, are you getting it? If there are valves, then these trainers, you can also look at them, okay, these trainers on the suction. So this is a thermogram from the mechanical equipment. This is for the pump. Are we getting it? So if this is normal, during normal operations, especially this is what you should be seeing. So you identify the temperatures here. So if something heinous is happening within the pump itself, you'll be able to see as it is happening. So you can see also another thermogram of the pump. Okay, so all of this goes to show us maybe if the impeller is loosed within the shaft inside, of course, apart from the vibration noise that it will create, okay, the vibration increase in vibration that you see also that the temperature will also go up. Okay, so on the bearing housings on electric motor, we have discussed this before. Okay, bearing housings on couplings, we have discussed all of these before. Okay, so still on mechanical applications, remember when we started this section, we looked at a tank that you can use the camera to know the level of fluid in tank. So all of these vessels, you can actually determine the level of process fluid in this vessel with the camera. Then all of these valves, the one that is passing fluid, you expect it to be short and it's still passing. You will see it clearly, especially if the fluid is hot that is going through the valve or through the line, okay, through these pipes. So passing valve, you can get it. Leaking valves, you can use the infrared camera to determine them. So you see, this is showing us that this valve is closed. Okay, so since it's closed, you will not see the process fluid flowing through. Are you getting it? Because it is short. Then this one that is open, you see the process fluid flowing through, because you have the thermal, the heat energy from both side. Okay, the upstream and the downstream of the valve being the same. But if it is short, you see that the upstream will be hot while downstream will be cool. Okay, all of that as you have in this case now, all of them will show on the thermogram. Okay, so this is another example. Okay, so you see that the valve is open. Are you getting it? So from apart from apart from the fact that you may know if the valve is open from the stem, okay, you can use this to determine if truly it is open, because at times you will open the valve while the disc will fail to lift. Are we getting it? So if the disc fails to lift, even if you have opened it, you will see that the valve will remain shut. So the thermogram will help you to confirm if the valve is truly open. Or if you shut and the stem did not move with the actuator, okay, you will see that even if you have shut, the valve is still open. So it is possible that it will be still passing process fluid. Okay, so this is another example. See that the valve is shut, hotter upstream, cooler downstream. Are we getting it? So this shows clearly that this valve is shut. So if you have sent a signal for it to open and it's like this, then you know there is problem with the valve. Okay, but if this is the normal, this is how it's supposed to be. You send signal for it to close and you are seeing this, which means it's closed. That means everything is fine. Okay, so this is a valve that is open, valve on a steam line that is open. Okay, so this valve is open, this one is closed. You see the upstream hot, downstream cool, upstream hot, downstream hot. Okay, so the one on the left is open and the one on the right is closed. So if that is their normal state, that means everything is fine. Then on still on mechanical equipment, like on compressor or reciprocating engines, the inspection holes around the top cylinders. If you have leakages, okay, sea breakage and what have you, so you see clearly that such leakage will show on the thermogram, okay, which is what we are seeing here, and which you will not see ordinarily with your naked eyes. So you see this is a compressor station, okay. So you see that around the first stage, okay, the compressed air before it goes to this particular vessel, okay, the surge drum. You see that here you see the hot compressed air, which is what is this is the normal thermogram. You see that the compressed air, because you are compressing, reducing the volume of the air or the gas, what happens? You see that you increase the temperature. So that increase in temperature is showing around these compressors, okay. So you see them before it is sent into the, that could be an intercooler or a surge drum, can't say for sure, but it is cool here, makes me to suspect that it is an intercooler. So we have the cooling water lines coming into it, okay. So it could be a cooler that helps to cool the hot compressed gas, okay, before it is sent into your process. So this also is a cooling tower, and you know that all the cooling water from your process as it's coming down to your cooling tower is expected to be hot, and that is what you are seeing, okay, that the inlet into the cooling tower, they are all hot. Are we seeing it? Then each of the cells, the ones that are working, you see the draft of hot air rising above each of those cells. So that shows you clearly that the cells that you are looking at of the cooling tower, they are all working. So these are some of the areas. It has a wider area of application even in process, okay. So you see this is compressed gas or liquefied gas tank. You see, merely looking at the tank, you will not know the level of fluid, but here you are seeing clearly from the thermogram the level of fluid in that tank. So you can use the infrared camera to also determine the level of fluid or liquid in a tank, as you can see here, okay. So when you have deposits around bends like this, okay, all of them will show on the thermogram, okay. So if you need to do something to remove them, of course you have to do it. So this also the level of liquid, okay. This is the sludge level, I mean to say, in a tank. So it can also give you the level of sludge that you have in a particular tank, so that you know if it is what you can still manage, or you need to commission your maintenance team to come and evacuate or clean up the tank, okay. So you can use it to also determine sludge levels in tank. Then this is your turbine, okay. So you see that all of these lines, you can use it to monitor insulated lines, the parts of these lines that have failing insulation already. Are you seeing them like hot spots on it? Okay, so you can ask your static static equipment team to re-insulate or to check it further. So you see that you with the infrared thermography you can get the condition of the insulation on those pipe and even on your turbine itself. So still on checking tank level, this is level is very visible here, okay, which is not visible on the visual image. Okay, still this is a three-phase separation tank. So you see this is showing different fluid. We have different fluid here, and of course we have different fluid here, which could be gas. Okay, denser fluid, less dense fluid. Are we getting it? So you see all of these different coloration, they represent different fluid in this vessel. Okay,